Working with rotation in processing, one of the key things to remember is that processing measures rotation in radians. Radians are a unit of measure similar to degrees. It would be kind of like talking about distance being measured in inches or millimeters or feet and meters. So it's two systems describing the same thing. With degrees, we have 360 degrees to travel around a circle. With radians, we have 2 pi radians, or approximately 6.28 radians to travel around a circle, because pi is 3.14 approximately. So we times that by 2. 2 pi is how many radians it takes to go around a circle, or 360 degrees. Most of us have grown up using degrees as a unit of measure. So we say, oh, I'm going to turn all the way around. I'll do a 360 degree turn. We don't say a 2 pi turn. It would be kind of funny if we did, but we don't. Because of that, it's useful to do your coding in degrees and then have processing just convert it to radians when you need to use that number for doing your actual rotation. And we can do that by using the radians method, which is built into the language. So we say radians, put parentheses, and then we put the value we are trying to transform inside that. Now, the first file we're looking at this afternoon is rotation. And when I run that, we see the square runs and disappears very quickly off screen. Oh, and then it comes back. And what you'll notice is the square is following an arc, and it's traveling around the origin point of our canvas, which is the top left corner, which is 0, 0. So you can see how it's traveling around, and for the time it's on screen, it now will be off screen 3 times the amount of time it's on screen, because this is 1/4 of the circle that we get to watch. So when we wish to rotate an object or multiple objects, unless we modify where is the point we're rotating around, they will be rotating around that top left corner, or 0, 0. I am going to modify my document here. I will comment out the first, uncomment the second, and now rerun this. And now what we will notice is the box is rotating around its top left corner, and that is rotating at a point from the middle of the screen. What has changed in my code, let me just pull that back real quick. What has changed in my code is I said translate x comma y. Now the place I just translated to is 400, 300, which is half of my width and half of the height of my document. So that chose a point right in the middle, and now that box is rotating around that point. So that's giving us a little bit more control. Now if I look at my box, I'm drawing a rectangle at 0, 0. Now if I drew my rectangle at something like -25 and -25, now when it runs, you'll notice that it is rotating around its middle, because -25 is half of the width and half of the height of that object. So we have translated to 0, 0, the middle of the screen, and then we said draw the box so that it's drawing the box offset by half of its width and half of its height. And by using that technique, we are now able to have objects rotate around their center points. Now, in the next example, as we look at this, we see that there is a sun, a planet, and a moon. The moon is rotating around the planet. The planet is rotating around the sun. We're able to do this because we have now translated multiple times, and we can store information about that transformation in a transformation matrix. And we do that by using the pushMatrix command. And when we say pushMatrix, we're telling the computer to remember how the world was before we started messing with it. Then I translate to the middle of my screen so I can draw my sun at 0, 0. Now, unlike the rectangle in the previous example, a circle by default draws around its middle unless we change the ellipse mode to be corner, where rectangles by default will draw from their top left corner. And the reason that we will typically leave rectangles drawing from their top left corner is when we switch to drawing images, those images draw from the top left corner just like rectangles. So that's why we haven't made a big push to just use the easy command of rect mode center to draw a rectangle around its center, and then it would automatically be doing that, which we could have done that in the previous example and then still drawn our object at 0, 0. So I translate to the middle of the screen. I'm choosing rotate R. Now R is saying I want to go 1 degree every frame of my program, so 60 degrees per second if we're running at 60 frames per second. Fill with yellow, draw an ellipse for the sun. Then I'm going to draw the Earth so that the Earth is rotating around this same spinning sun. Now you may say, well, how do I really know that the sun is spinning? And I guess I will say, well, you don't. But if I draw a rectangle at -50, -50, comma 100, comma 100. So if I draw a rectangle on top of the sun, it obliterated it. Sorry, I should need to make it smaller. But you can see now the sun is rotating and the planet is moving with the sun. Just make it smaller so we can get a circle and a square. We can see how the sun rotates. The planet is following the sun as it moves around. And then I say, well, okay, remember that. Now I'm going to translate the moon to a new location. And if you notice, the moon is rotating in an opposite direction from the direction of the planet going around the sun, because it is being fed a negative value, so it's always going to be in a negative direction. So if you rotate a positive radiance value, it rotates clockwise. If you rotate a negative radiance value, it rotates counterclockwise. And we can see that happening with the moon. Now, with the moon, we translated to a location. And that location is EX and EY. EX of 140, EY of 0. Now, as we look through what's happening here, EX and EY, well, that happens to be Earth X and Earth Y. So we drew the Earth. I'm going to kill the rotation here temporarily. Run it. So we can see when it's not running. Sun is at 0, 0. The Earth is at 140, 0 in relation to that 0, 0. So it's now moved over 140 from that new 0, 0 point, which was the center of the Sun. The Moon, we translate to the center of the Earth, EXEY, and then we push it further out, and we push it out 25, but we still keep it in a line. Now the Moon has a radius of 5. It rotates at a negative speed, a faster speed than what the main planet is rotating, because it's that amount times 3. So it's going 3 degrees for every one of the planet, which is why it seems to be going faster. If it was just simply negative r, we can see how it rotates, but in a much, we don't really get the feeling that it's rotating around the planet as well. So this technique of using the matrix and using translate allows us to have more control over drawing our objects on screen. Critical thing to remember is every time you say push matrix, there better be a corresponding pop matrix, otherwise the program will run out of memory. Because if you don't have a pop matrix on there, it's progressively doing that matrix transformation, and it will remember it from frame to frame. Once you do it, translate, it stays with it, even if you didn't have any more lines of code ever calling that. Nothing undoes it until we say pop matrix. So if I say push matrix, the program will crash if I don't have a corresponding pop matrix contained in it. So if I close that out, I'll say cannot push more than 32 times. So I didn't even make it a second. Made it barely a half second before it crashed because it tried to do it one too many times. So we need to make sure, and you'll find out the hard way, if you don't close your push matrix with a pop matrix, you will get that error message. You're like, what? Oh yes, whoops, I forgot. It happens a lot. If you get in the habit of, if you type push matrix, you hit return twice, type pop matrix, and then go back and put the code in it, just like doing curly braces, that will save you aggravation down the road. In this example, you will see that there are 3 planets. I see 3 planets on screen. I see 3 planets being described here. We don't specifically have a sun. One of our planets is the sun. It just so happens that that planet isn't doing anything. Now, if we look at the planet definition, we'll see that it takes a diameter, a distance, a speed, and a number of moons, or moon count. If I go back here, I'll see that the first planet is passed a value in, and that's going to be the diameter for that planet. Then I have 3 zeros, which correspond to its distance from the center of the universe is 0. Its speed is 0. And it has 0 moons. So it's now a fixed planet. Now what would be interesting is to, if we give it a speed, we'll notice how we can make it move. or I can make it rotate much slower than the other planets that are there. So if I want that to move, and the reason for approaching it in this manner is that there's really no reason that our sun has to be treated any different than a planet. It just has no moons on it. Unless you argue that the other planets are a moon, and then you could construct this a little bit differently. So I have an array of planets, 3 planets. One is a size 50, the next one is size 20, the next one is size of 30. Their distances are 100 and 200 respectively away from center point of the universe. They have their different speeds occurring and their number of moons. If I want more moons to occur on my planet, I could now give that second planet 5 moons. Looks like some of those moons, if that was a sun in the middle, would be burned up pretty quick, or it's a very cold sun. Now, after this, key thing is we're translating everything to the beginning of the front of the screen, and then we draw the planets, where we update and display each planet. Particular example, the moons are children of the planet. So the moons are being defined inside the planet so that they can inherit from the planet. That is why in our main class we see we only are telling the planets to update and display, not the moons, because the moons are being controlled by the planet. Update is just updating the rotation of this object by its speed. Then we rotate based on our current rotation. We translate out to what our distance from the center is supposed to be. Set the fill color. Draw the planet. And then update and display the moons. And then, of course, popMatrix. Now, when we look at the moon, we'll see that when a moon is created, it's given a diameter, a distance from the center, and its speed. So if I go back into my planet class, we will see that when a new moon is created, the moon is given a diameter, distance, and speed. Diameter, distance, and speed. If we want our moons to have more speed, we change these numbers. If we want less speed, we change them as well. If we want to change the diameter of the moons, we can certainly do that. Or, I'm sorry, not the, I mean the distance. So we could push the moons out. Oh. Now, if I turn off all the rotations, you will notice how we have the first planet, the second planet, the third planet, the second planet with its 5 moons, the third planet with its 3 moons. So we can see how when the moons are added to a planet, each moon is pushed a little 10 pixels further out from its neighbor. So we take the diameter, we add 10, and then spacing of 5. And then we repeat that, so the next time through it'd be 20 plus 5, then 30 plus 5, then 40 plus 5. So each time it makes sure that the moons are not on top of each other. So that's where the diameter plus I times 10, the I times 10 is creating a number that pushes each moon further and further out from its center point, and the center point is where the planet is being drawn. And the moons are super simple. They receive those values, so then they know how to draw themselves. They know what their rotation is going to be, they know what their speed will be, their diameter, and their distance from the middle. And we use that distance to be under a translate command. Now you will notice that pushMatrix and popMatrix doesn't automatically indent code. So in some of these, I'm taking it upon myself to manually do that. I believe that makes your code a little bit more readable. With these images, if we look at the planet class, we'll see that the planet class is being passed in the array of images names. My image array name is the variable I chose to call it. Inside my display function, we will see where it's being used. So I am telling it how many frames and what image array to use. So realistically, planet class is done. We don't even have to change it again. Moon you will have to change because there are no pictures in the moon yet, and I expect pictures in your project. So you're going to have to work on integrating those a little bit. But when I go here, we'll realize I'm passing in how many frames and the name of an image array. If we go back to when we were working on our sprite images and we had multiple animated sprites, we had multiple image arrays, one per sprite. We had one for the enemy, we had one for our sprite. Well, now we could have planet images 1, planet images 2, planet images 3, and if you have 8 planets, then you would planet images 8. And then if you have a dwarf planet like Pluto, then you could have planet images dwarf. Because we can't acknowledge it as being number 9 anymore. The scientists tell us that. They've robbed my childhood. So we have a load assets just like what we had inside our sprite images. So we will have a for loop to cycle through one, for loop to cycle through the other one, for loop to cycle through the third to populate each of those image arrays with the appropriate images. At that point, we just need to pass in the correct values. The planet class is done. The moon class will need some loving care to be able to show us those images. But when it's done, you will have a completed solar system with multiple planets, all unique and animated, and moons, all unique and animated, moving around those planets. Just going to do a brief explanation and looking at trigonometry this afternoon because math is fun. If you tell yourself that often enough, you might believe it. Because it is true. Math is fun. It can do wondrous things. When we are working with math, there's only a few things that we really need to care about, and as we're caring about it, a lot of it is going to be just using pre-built formulas or algorithms. We don't have to invent things from scratch. If I look at this red dot here, and if I imagine that is going to be my player, and it's moving off in a particular angle or direction. So if it's moving off in a particular angle or direction, so we can see, oh, gotta get away. Got a little chase action going here. Moving in an angle or direction. What happens is if we look at the red triangle, you will see that the red triangle has a horizontal component, it has a vertical component, and it has a diagonal component. Now my player, the blue box, is moving on that diagonal. So every frame I tell it to move a little bit horizontal and a little bit vertical while it's rotated at a particular angle. That is all that's happening. Now the cool part about that is this is a right triangle. So we are moving the hypotenuse. And if we say that just for theory purposes, that the hypotenuse has a measure of 1 inch, 1 foot, 1 mile, doesn't really matter. But we'll just say it's 1. Or in this, like in our little game, it's a speed of 1. Well, that means we can see our angle in degrees or in radians, and we can see how much I need to move on the adjacent line. The adjacent would be the horizontal, and the opposite would be the vertical component. How much I need to move to cover that distance on that angle. And that's the beauty of the right triangle, is by using the hypotenuse, opposite, and adjacent. If we know what angle we are rotated to, and we know how far or fast we want to travel, we can work with the 3 equations on top. So if we take the sine of an angle or the cosine of an angle, so the sine of the angle is the opposite measure divided by the hypotenuse. The cosine is equal to the adjacent divided by the hypotenuse. So when we're trying to figure out how much I need to move each frame, well, opposite, that's going to be my y, so we see that's a sine. So I take the sine of the angle, divide it, or multiply it by the hypotenuse, or the speed I'm traveling each frame, and then that tells me exactly how much I need to move on my vertical axis. I take the cosine and multiply that by the hypotenuse, and that tells me exactly how much I need to move horizontally. Now the hypotenuse is my speed, so that's just the beauty of the math that is happening. So when I look in my sprite, I will see that my sprite, if I push left, it rotates me left or right. If I push up, it now makes my speed increase until I hit my maximum speed. If I push down, nothing happens, but if I do nothing, then the speed will start slowing down on its own. So there's a little friction component. We'll look at that later. But we say I move on the x, the cosine of my angle times my speed or hypotenuse. I move on the y, the sine of whatever my current rotation angle is, times the hypotenuse or speed. So when we look at the scary math, go, whoa, sines, angles, and the reality is all we're really trying to do is figure out how much to move on the x-axis, how much to move on the y-axis each frame. And that's all the math is telling us. And then we update our object. And that really is all we need to be able to now move, can rotate. The enemy is rotating as well as the enemy is following me around on screen. And when we intersect, you can see how the whole world turns red, and it's really scary. So with that, we will be moving towards utilizing this and playing with that little bit of trigonometry. And these 2 lines are all we need. So when we look at the math and want to figure out the math to do it, if you don't do it for a while and you forget the formulas, the algorithms, you have 2 options. One, you can go Google them, and they're pretty easy to find. If you just do game programming, rotation, movement, it'll find it for you. Or you can start drawing out a triangle and remember SOHCAHTOA and figure out the trigonometry and relearn it in your head each time. Both are valid ways of doing it, and I will confess to having used both methods over the years.